So let's continue with what we left last week. We were talking about Lyapunov function. To make Lyapunov function works, I need the function itself to be positive definite in some neighborhood that containing x star. And then we need to check the sign for x prime. This x prime here is with respect to t, okay? If this is negative definite, then x star is asymptotically stable. If it is negative semi-definite, in other words, it's greater or equal to 0, then we simply say x star is stable. And one of the examples that we did last time is this one. So I'm trying to recall that example that we wrote last time. And the function we used was x squared plus y squared. Clearly it is positive, except it's 0, 0. When you do L prime, along the solution curve, of course, okay, along the solution curve, we end up with, well, we do the chain rule. So this dx dt, this term dy dt is this one. We simplify this whole thing, we get 2 alpha x squared plus y squared, and then squared. So alpha is negative, imply L prime will be strictly negative. In other words, negative definite. And that's what we say 0, 0 is asymptotically stable. Okay, so the origin is asymptotically stable. Let's quickly recalling what we did last time. Here's another example. Let's call this example number 2. Okay. Many of you can recall this is actually an example from what we call FGCU-Feng-MATH system. Where y is the displacement, so you have a spring with a mass attached to the end. There is some friction with the surface here, and there is spring constant k. The mass of this object is m. When you do second derivative of y, you get phi prime, which equal to this guy here. The phi here, of course, is y prime. So this ends up with a single equation about y. Multiply m across and move terms around. You get this second order ODE that you probably seen it before. That has constant coefficients m, mu, and k. Okay, m, mu, and k. So you should be able to solve this. Okay, But that's not the goal here. Okay, the goal here is to study the behavior of equilibrium, which is when phi is 0. When phi is 0, y is also 0. In other words, the velocity, will be 0. The displacement is also 0. All right, what's going to happen to the mass? So that's the problem. So what we're going to do here is, again, to come up with a Lyapunov function. It turns out the function that works in this case is given by this. And if you look at the function that I have here, 1/2 m times my velocity squared, this is actually some kind of energy. This is the energy from the movement. 1/2 ky squared. That's the energy kind of stored in the spring, I guess. Ky squared. It's pretty trivial. This is positive definite. With a minimum at the equilibrium 0, 0. Okay, with the minimum at 0, 0. Now let's go ahead and calculate the time derivative. That's not too hard to calculate. Differential with respect to y, you get ky. And y prime, okay, y prime is phi. Differential with respect to phi, you get m phi. And dv dt is given by this term. When you FOIL things out, this turns out to be negative mu phi squared. Now here we're assuming if this is a spring mass system, the mu here is always a positive constant here. So this is clearly less or equal to 0 if mu is positive. Thus we say 0, 0 is stable. Okay, it's stable. Okay, so that's this one. So this is an additional example about the upload function. Obviously, it is very tricky to create the upload function, and only after you practice so many problems you can have some intuition. And I'd like to wrap up this section with the following important concept: the so-called omega limit set. Of a solution, okay, the omega limit set of a solution that we denote by x, capital X, which is obviously a function of t. It also depends on the initial data. So picture this capital X to be a trajectory on the xy plane, okay, to be a trajectory on the xy plane. The omega limit set refers to the collection of all the points such that there is a time sequence. There's a time sequence, and as n goes to infinity, the solution, okay, the solution approaches this point z for some time sequence, goes to infinity. So this gives you the long-term behavior of the solution, right? It approaches a point z, okay? All those points z is called the omega limit set. Such set is denoted by omega limit set, so I'll use omega here. And it obviously depends on the x naught, okay? Depend on where the solution curve starts. Different starting point, we have different omega limit set. Alpha limit set is somewhat the same concept. It's just the time t goes to negative infinity. So this is the set of solution where the solution approaches point z when t goes to negative infinity. So I can still write like this. There's a sequence. For some sequence t sub 1 goes to negative infinity. So this is going backwards in time. Such set is alpha limit set. Alpha limit set is our primary concern in our next chapter, but this is where you hear it today. Okay, this is where you hear it. To give you some example, I can make a very simple sketch next. I'm going to make a simple sketch. Oops. So here is an initial point. As time t goes to infinity, let's say this is how the trajectory looks like. And that could move into an equilibrium that I call, say, E naught. The other half of the trajectory, going backwards in time, it could be a different equilibrium. Then for this trajectory, we say the omega limit set will be the point E naught, because that's the only point. The alpha limit set will be another equilibrium, E1. Alright? Here's another different example. If the trajectory looks like this, that somehow appears to be approaching a closed orbit. Like there's a closed orbit inside. The trajectory is moving closer and closer and closer and closer to this closed orbit. So in this case, it's not approaching any fixed point. It's not approaching any fixed point. Instead, it's getting arbitrarily close to this closed orbit that we call gamma. Then the omega limit set will be this set gamma. Going backwards in time, okay, going backwards in time, this guy can come out of a equilibrium point, say E1. Then the alpha limit set will be E1. Okay. So the structure of omega limit set and alpha limit set, you know how what kind of points or what kind of sets should be in there. That's the goal in our next chapter. Okay, in our next chapter. But this wraps up 9.2. Okay, 9.2.